These are the notes for the Concavity II worksheet. So we're going to start with a graph of the derivative of f of x. So we don't know what f of x looks like, but we do know that this is the graph of its derivative. So the easy question is, if we're looking at the derivative of f of x, where is the relative maximum? Well, right here is the relative maximum. So this is the graph of the derivative, and it's asking where's the max, relative max for the derivative. So it's right here. So this is at 1. The relative min, well, nowhere in here are there relative mins because we keep going down. We have absolute mins at negative infinity, but the relative min we have none. And an inflection point is where the concavity goes from concave up to concave down, or vice versa. And again, we're looking at this for the derivative. So where's an inflection point on the derivative graph? Well, this is, as we travel up here, this is all concave down. This is still concave down. So right in here we're concave down. Over here we're concave up. So we've switched between here and here. We switched from concave up to concave down. So somewhere in here there was an inflection point. We could say that it was at 2. And there's a second inflection point here at 4, because here we are concave up, and past 4 we are at concave down. So exactly at 4 we're switching from concave up to concave down. So the second inflection point is at 4. Now the tougher question is, what's going on with the f of x graph? And again, we can't see the f of x graph. All we see is what we have over here is the derivative graph. So we're looking for maximums and minimums. Maximum and minimums we get from analyzing, doing a line analysis of the first derivative. So I'm actually going to do that right here. So what does the first derivative tell us? Well, the first derivative is 0 at 0. The first derivative is 0 at 4. And in between, oops, that wasn't a very good 4. Let's start again. So again, these are critical points here. Critical point at 0, critical point at 4. To the left of 0, the first derivative is negative. To the right of 0, the first derivative is positive. To the right of 4, the first derivative is negative. So if our first derivative is negative over here, and then it switches to positive, that means we were going down, and then we now are moving back up. So 0 must be a min. So we have a minimum at 0. And then if the first derivative is positive, it's going up, and then at 4 it turns around and starts headed back down. That must mean we have a min at 4. And now the inflection point is where the concavity of the function, the original function, f of x, where the concavity changes from concave up to concave down, and we're interested in the concavity of this original function. So I'm going to do a line analysis, number analysis, for the second derivative. Okay? Now the second derivative is the derivative of the first derivative. So if we look over here, the second derivative, as we're moving here, these are all positive slopes here, positive, positive, positive slope all the way up to 1. So these are all positive slopes up to 1. At 1, we have the slope is 0. The other place the slope is 0 is at 4. So we have 2, what we're referring to as dire points. So we have 2 dire points. One of them is at 1, is over here at 4. And then to the left of 1, these are all positive slopes. So if we have positive second derivative, that means that we are concave up. After 1, between 1 and 4, right, all of these, this is actually down to, these are all negative slopes. Second derivative here is going to be negative down to 4. So if we have negative slopes, then we are at concave down. And then beyond 4, these continue to be negative slopes. So beyond 4, the second derivative is going to be negative. Again, the second derivative is the slope of the first derivative, so these are all negative slopes. So then that means beyond 4 we are also concave down. So 1 and 4 are dire points, and at 1 we switch from concave up to concave down. So then that means that we have an inflection point at 1, and at 4 we switch from concave down to concave down. So there is no switch. So 4 is a dire point, but it is not an inflection point. So now what I want you to do is pause the video and read down here part 2. Take your time reading through this. Make sure you understand all of this. Make sure that in particular you understand these 3 bullets here. And then when you're done reading, you can start the video up again, and I will join you working on example 2. Right? So read part 2, and then we'll work on example 2. All right, so you're back from having read part 2, and we'll start in on example 2. All right, so in example 2, we need to find the intercepts of this function. We need to find the extrema, the max or the min, and we need to find the inflection points. So we get the intercept by looking at the function itself. So we can figure out, first off, if we plug in 0 for x, you're going to end up getting 0. So we know that we have this point here is on the graph, 0, 0, because that is our y-intercept, and it also is our x-intercept, or one of our x-intercepts, right? So we have a y-intercept at 0, 0. Now the x-intercepts will be when the function itself is 0. We can factor out an x. That leaves us with 1/4 x to the third minus 1. Using the zero product property, we want either this factor, x, to be 0. Well, we already have that. That's this point right over here. Or we want this here to be 0. In order for that to be 0, what we need is we need 1/4 x to the third minus 1 to be 0. And that's going to happen when x is equal to the cube root of 4. And the cube root of 4 is approximately 1.6. So I'm going to put that other point right over here. Right? So we've got, it's roughly 1.6. So we've got our intercepts. Now to get our extrema, we need to take the first derivative. So we'll take the first derivative. So the first derivative is going to be equal to x to the third minus 1. We're going to do the number analysis here for the first derivative. We're going to be looking for when the first derivative is either 0 or undefined. We're looking for critical points. There is only one, which would be 1. And then we want to look to see what's happening to the left of that, what's happening to the right of the critical point. So to the left, for values that are less than 1, we will end up getting a negative slope. And for values that are greater than 1, we'll end up getting a positive slope. So that means that if we're going, the slope is going down, approaching 1, and then it goes back up after 1. What we've just found is we've found a minimum. And the minimum is going to be at 1, comma, and then we take the 1, we plug it back up here into our original equation. 1 to the 4th is 1, 1/4 of 1 is a fourth, minus 1, and this is going to give us negative 3/4. So at the point 1, negative 3/4, we end up with so that's our point right there, roughly. So that's the only extrema we have, which is a minimum right there. And then last bit is to figure out the inflections. And the inflections are when you're switching concavity. In order to figure out about the concavity, we're going to need to take the second derivative. So the second derivative is 3x squared. The number analysis for this, we want to find the dire points. Dire points are where the second derivative is either going to be 0 or undefined. There is only one dire point. That dire point is at 0. And to the left of 0, the second derivative is going to be positive, so this will be concave up. To the right of 0, the second derivative is going to be positive also, so it'll be concave up. And then means that we have no inflection point. So we have no inflection point. And what's happening is we have concave up, and then at 0, there's a pause in the concavity, if you will, which would mean that if there is a pause in the concavity. If the concavity is 0, that means it's not concave up, it's not concave down, which means it's linear. So it's exactly 0. We have this graph ending up sort of pausing, having a 0 slope. So that means that if we're not changing concavity, then at 0, 0, at 0 over here at this point, what we have is we have something that looks linear. And we know, looking at the first derivative, actually we could figure out what the slope is at the first derivative, right? So we plug in 0, it's going to have a slope of negative 1. So we know that this graph here, right in here, a little off there, but its slope at exactly 0 is going to be negative 1. And to the left of 0, its concavity is going to be concave up. So I missed that completely. Sorry, I'm trying to get these to line up. Having a little bit of trouble here. Sort of like that. It's going to be concave up going this way. This in here is also concave up. And then we know that past 1, the slope is going to stop being positive, and it's going to stop being negative past 1, and it's going to end up being positive. So then we know that from 1, we're going up through 2, 0, and up like this. So this looks very much like the graph of x to the 4th, except that right in here, we have sort of this flat spot to it. All right? All right, moving on with our notes. Okay, so here, part 3, what we've done in the past when we found a critical point is we figured out where the first derivative was 0 or undefined, and then we looked just to the left, and then we looked just to the right to figure out what was going on with that critical point. Was it a min? Was it a max? Was it neither? We can do the same thing by using the first derivative, the value of the first derivative, and the value of the second derivative. So we're going to do this here for example 2. And so the value of the first derivative here, right, tells us that we have a 0 slope. And could be a critical, it is a critical point because the slope is 0. It could be a min, it could be a max. The value of the second derivative here tells us that we are concave down. So if we're concave down and we have, we know we're concave down at 3 and we know that we have a 0 slope at 3, that must mean that this graph looks like that, roughly, which means that we have a max. And we did not have to do a number line analysis in order to figure out that at 3, the function f of x has a max. So this is referred to as the second derivative test, which is an alternative method for determining what's going on with these critical points. So here are the notes that goes with that. So if you have, right, so we're starting, here's the condition. The second derivative test only works when we're looking at a critical point for when the first derivative is 0. So if the first derivative is 0 and the second derivative is greater than 0, if the second derivative is greater than 0, that means that we are concave up, right? So that's what that's telling us. So if we're concave up, then it must look like this, and that means that we have a min. If the second derivative is less than 0, that tells us that we are concave down. Right? So the second derivative is telling us that we're concave down, so we know that it's looking like that. So that means that we must have a max. And then finally, if the second derivative is 0, what that means is that we have no change in concavity at that point. If we have no change in concavity at that point, we have something which is linear. So that could be that we are horizontal. It could be that we have positive slope, negative slope, whatever. But we just know, all we know that is it's linear at that point. So we can't determine the nature of the critical point. Okay? So let's do a couple of examples here. So example 2. So if we take the first derivative of this function here, so the first derivative is 2 sine 2x, 2 sine 2x minus 2x. And we know that what we're interested is in what's going on at x equals 0. So we're going to look for the value of the first derivative at 0. So we'll plug 0 in here, and what we get is 0. This tells us that we have a critical, can't spell. I'm having a hard time writing with this stylus, which makes it harder to spell. Critical point. Now we are going to look for the second derivative. So the second derivative of this function is going to be minus 4 cosine 2x minus 2, and at 0, the second derivative is negative 6, which means that we are concave down, and then the conclusion for all of this is that these two pieces together tell us that at x equals 0, we have a maximum. Okay. Example 2. New function. We're looking at this here. What we want to do is show that the curve has a horizontal tangent line at 0, 3. So to show that it's got a horizontal tangent line at 0, 3, we've got to do two things. The first thing we got to do is we have to verify that the point 0, 3 is on the curve. Right? So first thing we got to do is make sure this is on the curve. So we're just going to take that point 0, 3 and plug it in to this equation and make sure that it actually makes this equation true. So when I plug in 0, 3, so this would be y squared minus y, that's going to have to equal 3 times x squared plus 6. This is going to be 9 minus 3, which is going to equal 6, and yes, indeed, it's on the curve, on the graph. So the second thing we have to do is we have to make sure that it's going to have a horizontal, right? We want a horizontal tangent line. So if the tangent line is horizontal, then that means that the first derivative has got to equal 0, right? So we want to verify that the first derivative, actually it's the first derivative at x equals 0. We want to make sure that the first derivative is 0 at x equals 0. So in order to do that, I need to find the derivative of y. And in order to do that, I'm going to do implicit differentiation. So I'm going to take all of this, and I'm going to dx, the entire thing. So I'm going to take the derivative of this equation, and then I'm going to solve for y prime, or solve for dy dx. So this is going to look like 2y dy dx, the first term, minus dy dx, which is going to equal derivative of 3x squared, which is going to be 6x, plus the derivative of 6, which is just 0. So now I'm going to solve this by factoring out the 2y minus 1. Leaves me with dy dx is equal to 6x, which means that dy dx is equal to 6x over 2y minus 1. And then I'm interested in what's going on at 0, 3, so I'm going to plug those 2 points in. So I'm going to get, at 0, 3, we're going to get, at 0, 3, we're going to get 6 times whatever the x value is. The x value is 0, all divided by, and at this point I don't care what's in the denominator because the numerator is 0. So then I know that dy dx is indeed 0. Right? So the slope at 0, 3 is indeed horizontal. So I've done part A. Right? So now moving on to part D. Right? So we're going to use the second derivative test to determine what type of critical point it is. And just a little bit of notation here. This is another way of writing the second derivative, and Mr. Friedland has no idea why we write it that way, but I believe it has something to do with the fact that you're taking the derivative of a derivative, and then the same thing when you multiply, and then multiply again, we end up with an exponentiation. This is sort of language of exponentiation, doing the same operation twice. So I'm taking the derivative twice. So the derivative, then what we need to do, I need to get back so we can see this previous, right? So what I need to do is I need to take the derivative of this. Now, this is a quotient, so I'm going to end up using a quotient rule. Right? So I'm going to write this with this notation, second derivative. So we're going to do the derivative of 6x over 2y minus 1. So we need the derivative of the first, which is 6 times the second, 2y minus 1, minus, I'm doing the quotient rule here, the first, 6x, times the derivative of the second, which is going to be 2 dy dx, and that's it. And then we're going to take this whole thing and we're going to divide it by the square of the second. So this would be 2y minus 1, the quantity squared. Right? And now at this point, we have, in here, we have all of these values, right? So we're interested in what's going on when we're at 0, 3 on this function, right? So we know what y is. Y is 3. We know what x is. X is 0. We know what dy dx is at this point. That's 0. And we know what y is. So we can plug in all of those values and evaluate. So we're going to get 6 times 2 times 3 minus 1 minus 2 times x is 0, 0 times, and at this point I don't really care what dy dx is. Turns out dy dx is also 0. I already know that this term over here is going to be 0, so I can stop calculating that and just worry about what's in the denominator, and the denominator is going to be 2 times 3 times 3 minus 1, that whole thing squared, and when we evaluate this, we get, this is 30 over 25, which is greater than 0. So if the second derivative is greater than 0, then we know that we are concave up. And if we are concave up, then we must have a minimum. So the type of critical point here is a minimum. And we're now done with notes.